Welcome to this video lecture on estimating a standard deviation. You will already be aware that to estimate the standard deviation of a population, we use the sample standard deviation estimate S, which is based on n-1 degrees of freedom. This estimator is an unbiased estimator of sigma. It is of course necessary to divide by n-1 in the calculations and not by n. And the reason we do this is that the deviations between each value and the mean should be measured from the population mean. But the population mean is typically not available to us. And so we measure those deviations from the sample mean. And so the deviations are too small because those numbers are closer to the sample mean than they are to the unknown population mean. So because the deviations are too small, by dividing also by a divisor which is, in a sense, too small, n-1 rather than n, we compensate and make that correction so that S, using n-1 degrees of freedom, is an unbiased estimator of sigma, the population standard deviation. Now, that's how we estimate sigma from a single sample, but sometimes we have two or more populations that are known or assumed to have the same standard deviation. And so if we have samples from these different populations, we can put all the information together by pooling the samples in order to get a pooled variance estimate. In practice, this is often done just to simplify calculations. We sometimes assume that variances are equal, and we pool the information about variances from different samples to calculate what we assume to be the common standard deviation across those different populations. If the sample sizes are the same, then of course we can simply get the mean variance. And taking the square root of the mean variance gives us the standard deviation. If the sample sizes are unequal, then we have to construct a weighted mean, giving more weight to the sample which has a larger number of degrees of freedom. And so we have this formula that we use for two samples from two populations which have an assumed equal variance. S squared, the pooled variance estimate, is n1 minus 1 s1 squared plus n2 minus 1 s2 squared, where n1 is the sample size for sample 1 and s1 is the standard deviation for sample 1. Then n2 is the sample size for sample 2 and s2 is the standard deviation for sample 2. So we construct this weighted mean, giving more weight, as you can see, not just in proportion to the sample sizes, but in proportion to the degrees of freedom. So an example of the use of that formula is this one here. We use a depth sounder to take a number of repeat measurements at a point near the coast and to take a number of repeat measurements further out to sea. Now the depths involved are different, but we assume that the standard deviation is the same because the standard deviation depends on the precision of the depth sounder. So there we have 3 numbers close to the coast and 6 numbers out to sea. So in the case of each of those samples, we calculate the sample standard deviation estimate. And so we get, for sample size 3, n1, we get an s1 of 1.528. And for the sample 2, n2 equals 6, we get s2 is 1.169. So we have 2 different estimates, and somewhere in between those 2 numbers is the best estimate of the common standard deviation. So we apply the formula using weights of 3 minus 1 and 6 minus 1, and we get a variance estimate. We always do calculations with the variance rather than the standard deviation. So we get our variance estimate and then take the square root to get the pooled standard deviation estimate, which is 1.282, which, as you can see, is in between the 2 estimates, and it's somewhat closer to the estimate that arose from the larger sample, or I should say, from the sample with a larger number of degrees of freedom. Now, we may wish to construct a confidence interval for the standard deviation. And we do that using the chi-square distribution. The chi-square distribution is a non-symmetric distribution which is bounded below by 0, and it has a different shape for every different number of degrees of freedom. And so we can construct a confidence interval using the upper 2.5% point and the lower 2.5% point of the chi-square distribution. This provides us with 95% confidence that the standard deviation lies in the interval. It's worth pointing out that this is not a symmetric confidence interval. the confidence interval will be wider on the upper side because this is a non-symmetric distribution. So the point estimate will not lie halfway between the two limits that we will calculate in this way. So there's our formula, and we apply this to this problem. We have 5 loaves and their lengths are measured in centimetres, as shown. We'd like to estimate the population standard deviation with 95% confidence. So we have our sample size, n equals 5, our sample standard deviation estimate, 1.898, and we have n minus 1, which is 4 degrees of freedom. We look up the chi-square tables, and I will show you those in just a moment, and we get the upper and lower 2.5% points, which the tables give us 11.143 and 0.4844, and I'll show you those on the next slide. We then substitute each of those in turn into the formula. Substituting the larger number, 11.143, gives the lower estimate, 1.137, and substituting in the 0.4844, the smaller number from the lower 2.5% point, gives us the larger estimate, 5.454. So we can say with 95% confidence that the standard deviation of the lengths of all of the loaves lies somewhere between 1.137 and 5.454. And again, I'll just point out to you that the upper end of that confidence interval is a good deal larger than the point estimate. Now, how we use the tables is like this. Here are the tables of the chi-square distribution. Based on our degrees of freedom, which is 4, we use row 4 in the leftmost column, the degrees of freedom column. We go to row 4. So we will be reading values from this row. The values that we will need are the upper 2.5% and the lower 2.5% point. That's the 0.025 point, the third last column, giving us 11.143, and the 0.975 point, which is 0.4844. So we take those numbers from the table with the appropriate number of degrees of freedom and calculate the confidence interval in that way. You can read about this and attempt some problems in the textbook in section 4D.